Okay, so here we are looking at a distractible person on a bicycle waving to a friend and not paying attention to where they are going. Apparently, distractible is not a word according to OneNote. Weird, because I should look that up. Anyway, as a result, their tire hits a high curb, stopping the bicycle in very short order. All right. And for A, in this question, we're saying the person is launched over their handlebars as a result of this collision. Why does this happen? Describe in terms of Newton's laws in your written work. Note the law that is most applicable here. All right, so the most applicable here, I think, is the first law in terms of the bicyclist's motion, not the bicycle. Okay, first law. And that's so object in motion tends to stay in motion is the short version of that. And so bicycle stops, but cyclist isn't firmly attached and continues at the previous velocity, at least for a short time. Okay. So this is similar to like, I don't know, there was a concept question on assignment, I think, of someone having like a cake in their front seat. And the cake in the front seat, if it's unsecured and they slam on the brakes and the cake in the front seat maintains its velocity more or less and just piles up into the footwell on that side, it makes a big mess. And so the idea here is that the tire of the bicycle is the thing that's feeling this big force from the curb that brings the bicycle, right, because the tire is very firmly attached to that, to a screeching halt. But the cyclist, unless they are really strapped in, okay, to this bicycle, which you usually are not, they are going to be launched out of that seat up and over the handlebars. And sure, they're holding on, so they won't, preserve all of their velocity, but they keep moving for a time. This honestly is probably better than them coming to a halt, because if you have that abrupt of an acceleration, it can be quite damaging to you. I mean, not that this won't be, but perhaps less so. All right. So the first law is most applicable. You can make arguments about the second law and things like that, but in terms of the actual, okay, this person is launched over their handlebars, that part of the motion, that's definitely them continuing at their previous velocity. And that's definitely the first law. Okay. Now in B, what is the relationship between the force of the bicycle tire on the curb and the force of the curb on the bicycle tire? All right, so that is set up in a way to be reminiscent of Newton's third law, right? And the third law tells us that those two forces, so the force of the curb on the tire has to be equal in magnitude to the force of the tire on the curb, and in opposite directions, right? So the curb exerts a force on the tire. So if that's the tire and that's the curb, then the tire is feeling a force this way. So there's the force of the curb on the tire. And the curb itself, though it's not really going to move much in response to this force because it's quite heavy and attached to the earth pretty firmly, the force of the tire on the curb is off in that direction. This one, though, of course, has a profound effect on the motion of the tire and then the bicycle, and supplies the deceleration that you observe when you smack into a curb this way. All right, and lastly, part C. In your written work, draw a free body diagram of the bicycle as it collides with the curb. Assume that the person is still in their seat for the moment. Okay. Which force is responsible for the rapid deceleration of the bicycle? Well, we've kind of talked about a little bit of this. I will do my best to, let's see, what is a bicycle even? And then some handlebars here, and a cross piece, and bicycle. Okay, something like this. All right. So we have our bicycle, specifically the bicycle here, and not the person on it. And when we look at that free body diagram, well, we're going to have that force from the curb on the tire. I'll even call it the same thing I did when I was drawing that diagram in B up here, this one. So curb on tire. This thing is responsible for deceleration. And then there's probably some other forces, right? There's maybe like a little bit of rolling friction, so we call F sub F. There's going to be a normal force of the ground on the bicycle. There'll be some force of gravity on the bicycle associated with its mass. And then in addition to that, there's going to be a force of the, so the bicycle holds up the bicyclist, and so that normal force that the bicycle exerts on that person is exerted back, because of the third law, on the bicycle. So you'd have some little downward force here, force of, I don't know, cyclist. Okay, something like that. And you could even think about including like a force of friction between the cyclist and the seat and all that kind of stuff. But these are the basics, is what I'm looking for here, okay? So I think that brings us to the end of this problem. Hope you understood it. I'll move on to the next one.